Some of them some of these viruses will be killers. Some of them won't. How do we work that out from a viral sequence? It's not straightforward. So as an example, first of all, we're only looking at viral families that include those that have got into people from animals. So we narrow it down straight away. Then when you get a sequence of a virus and it looks like a relative of a known nasty pathogen, just like we did with SARS, we found other coronaviruses in bats, a whole host of them. Some of them looked very similar to SARS. So we sequenced the spike protein, the protein that attaches to cells. Then well, I didn't do this work, but my colleagues in China did the work. You create pseudoparticles, you insert the spike proteins from those viruses, see if they bind to human cells. And each step of this, you move closer and closer to this virus could really become pathogenic in people. So you narrow down the field, you reduce the cost, and you end up with a small number of viruses that really do look like killers. Then you look in people and you say, in the people that live in the region where this animal lives, that are exposed to that virus, do we see antibodies specific to that virus? There's the first evidence, just as the groups out in Cameroon are showing, of a new virus spilling over into people. What are they doing? What's the high-risk activity? Can we find an alternative? So it's not straightforward, but there are ways we can hone it down. And I think we've just got to do it. It just makes sense economically and for humanity's sake.